So we go back to our textbook here. So the chapter 6, we are talking about the pitch. So pitch is a long-term prediction. So in the traditional way, we can use in the time domain to find the pitch. So in time domain to find a pitch, they could be using the very easy way. We talking about this one. First one is more like a average magnitude difference function. So that one is just move your waveform like a tau here. So it's more like a tau is look like a from the 16 point to 116. What's the tau here? So you have a speech signal. So you have a speech signal here, and then you have a waveform. You have a speech friend. So you partition many speech friends. So regarding this speech friend, so you are moved from the 18, from the 16 to search to the 100, like a 116. So this one is your tau. So we are moved whole waveform, like here, 1 point, 17, 18, up to the 116. According human being, what's the pitch range? Because the human being, we are cannot pronounce very quick, or sometimes we are pronounce very slow pitch frequency. Sometimes you have some specific range, reasonable range for human being human being voice. So we try to hold speech friend, try to do the mapping, and then you can see if I give the example right here. So if I move like this space, so if tau move around here, so this frame move around here, so we can perfect match, almost match. So we can get a good we can make the distortion lower. So this one, because they have a positive and negative, so they using the absolute value. So you can see they're using the absolute value, trying to summation to become one speech friend. N is your number of speech friend, number of sample. N, so N is number of your sample. So like your sample, number of sample in a speech friend. So this one is time domain. It, so you can see their example here. So you can see the minimal distortion. We try to find the minimal distortion. This one is your speech waveform. We try to move around the one pitch so you can see the minimal distortion. However, you can see another one. This one is a double pitch. So this one is tau. This one is 2 tau. So it looks like we move two times of your pitch. So you can see we also can get a little bit absolute value. And sometimes we are considered because you are talking some area will be high energy, and some speech friend the energy become lower, but your gratis will be triggered. Maybe the pitch period could be similar. However, what you're talking about, maybe sometimes you are using large amplitude, and sometimes you're using very low volume. A low volume, sometimes a high volume. So we try to overcome this kind of volume difference. So we are given the beta value here. So another, they cite some paper, what's the best match in K? So could be they say, well, if we are using the mean square error, could be it's good enough. we do not need to use in the high order. So some paper do some study on this 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 area. So you can see, well, second order is good enough. Okay, so this one we derived before. If you are trying to move some autocorrelation, if you are trying to move the tau and multiply by beta, so this one is one tap. So we are move the waveform to the tau, and this point will be according the neighboring the sample to do the prediction. If we just only one sample to do the prediction, multiplied by beta, only one beta, so you can come out the equation, your cost function. So we are based on fix the tau because we have a two variable. So we are assume the tau is a fixed number, and then we take the partial derivative according to beta. We assume to become 0, so we can get the minima value. So you can see the condition beta equal normalized autocorrelation. So it's normalized autocorrelation would be the correlation and normalized by energy. So we will be get the better performance. So you can see we try to find the maxima one. So you can see the normalized autocorrelation. This one could be get a better pitch value. However, you still have the double pitch here. So this one is the autocorrelation. If we are consider normalized autocorrelation, consider the energy. So this one would be looking like a little bit better. Normalized autocorrelation is like it's not an autocorrelation. We are consider divided by your energy. That shifting frame. That at that moment, speech frame energy. So you can see this one, what we derived before we have previous chapter, we already derived this one. If we are based on the equation, which one? If we base on this equation, so if we base on this equation, and assume tau is fixed, and according to beta, we take the partial derivative equal to 0, so you can get a beta. You can get a beta condition. You can get a beta. You can beta equal to this value. We can get a minima distortion, and then this beta will be substitute back your cost function. So you can get your cost function. You can get your cost function like this one. So you can get a cost function like this one. So if we try to minimize your distortion, so this one is your signal energy. So we try to minimize this distortion. So we have to maximize the second term. We have to maximize your second term. So this one is our normalized autocorrelation, more like a normalized autocorrelation. So you can see this one, what we did in the standard, some standard, try to adopt this kind of approach, try to find the pitch location. However, in the other way, you also can take the square calculation the other way, the similar. Okay, the first one we're talking about is time domain. Another one in frequency domain, we also can find the pitch, because your signal, this one in time domain, for each speech frame in frequency domain, so you can see they are harmonic. So envelope shape is related. This one envelope shape is related LPC. And harmonic. So you can see we have many harmonic. This we call the harmonic. Is a harmonic. So this harmonic is related to your pitch. So harmonic is related to your pitch. So we can based on the frequency domain, we try to find your harmonic component. So you can see this one is very straightforward. They're using the comb filter. So more like a comb filter. So more like this one. So more like your comb filter. So in the morning, maybe try to shadow your hair. So using the comb. So this one is a comb filter. They try to match your embryo peak point. So you have a lot. I make it bigger. Harmonic. So you have a comb filter. They try to make the peak point according close to your peak point. So because they are standard deviation, so they try to make sure what kind of spacing comb filter we can get a summation. We sample the point and can get the maximum value. If we sample the point close to their maximum, like alignment, their harmonic, they could be we can get the best value, the high value. So you can see here only related some omega 0. This one omega 0 we are in time domain. We are search area. Search region is 16 to 160. In frequency domain, this one could be some omega 1, and this one could be up to the omega like a 100, like a 50 minus 145. I'm not sure. 6 is 4, 5, and 44. So total is from 1 to 144. So we have many angle, many omega value. So we are search so many omega value. So we are based on different omega value here, and then only that one we have just have value. The other area will become 0. So we are trying to do the multiply then, and you can see if we are match. So we are trying to sample. We try to sample your embryo. So if we are alignment your peak point, so we can summation get a big value. So if you have a right harmonic value, so you can summation good value. However, sometimes because that one you have to the number you are summation so many number you have to divide it back. So some of the small harmonic you'll be sample more data. So you have to divide it how many sample you are summation. So you can see we are divided by this one, and also in frequency domain we have the other issue is double harmonic. So double harmonic is a half of pitch. So this one in time domain we will find the T, O2T, O3T, and so on. In frequency domain we will find the harmonic omega 0, omega 2, omega 0, and 3 omega 0. Because you can see like this one we have this one is signal frequency. If we are comb filter like a tech 2 omega 0, we still can sample. This one is 2 omega 0. We still can sample their peak point, and then the sample number is relatively small. However, we are divided back. So this one is dividing number of your sample data. So you can see sometimes will be find double harmonic. So double harmonic is related to your half of pitch and one of third of a pitch. So you can see in frequency domain, we find out sometimes will be mixed with the half of pitch. In time domain, sometimes will be find out our pitch will be double the pitch because depend on your method. So another one, this one is just comb filter. Another one is synthetic. So we are using synthetic model because you have many harmonic. So you can see this is your frequency domain waveform. If we can using the many harmonic, they can using many harmonic. We can use many harmonic to do the combination. So you can see we are consider your harmonic bandwidth. What's the harmonic bandwidth? So we are trying to use many harmonic multiply. We are sample based on that kind of harmonic. We sample your signal amplitude. So we are combine them together, become synthesized original signal. So this one is called a synthetic approach. So maybe I'm using the other way. For example, your waveform may be like this one. Okay, so if we are using synthetic, so maybe we can use in the like a sync function. If we have some sync function here, so we define this one how width of them. So this one is define how big of them. So maybe we using the bigger to, and then we are using this one try to sample their some data. Sample the data become our A0, A1. We are sample original waveform, spectrum waveform, and then based on our basis to become synthesized. So we are become synthesized. So according to this one, we become synthesized. So they are according your sample amplitude to do the synthesized waveform. And then if you are similar like your omega 0, sorry. So this one is our original. This one is our like a W. This one is your W. According to your omega 0, determine how big of a harmonic frequency bandwidth. So you can see, and then we are also try to sample your amplitude based on your harmonic frequency, sample original signal, and then normalize your unit amplitude, bandwidth amplitude, so become the sample amplitude. So you are synthesized. So you are doing the synthesize the waveform and try to see, what's the fundamental frequency we synthesize spectrum waveform more closely to original spectrum waveform. So this one is based on synthetic spectrum. Okay. Also, we are consider and time frequency domain pitch detection. So you can see here, this one synthetic and original waveform. So depend on how determine. So dash 9 is their original waveform, and 39 is synthesized. They have many omega, and then according original waveform, they are sample the peak point. So they are combine them together. So you can see synthesized, synthetic, and original waveform. If you are the basic, the fundamental frequency is a match original signal fundamental frequency, so you can get the best match, and then the distortion will be lower. So this one is what we're talking about. The normalized is a spectrum autocorrelation. So you can see also we can consider spectrum autocorrelation based on you have many synthetic, so you can have many window. So we also can consider the spectrum domain autocorrelation. So this one just show you what they did. Okay, so I'll make it smaller. So you can see here. What we have because we have a speech signal. So speech frame only 34. So this one is a short spectrum. Because the window size is smaller. So this one is a window size smaller. So you can see this one A is original waveform. So we have so many samples, but we are consider 34. The pitch is 34 samples. Sorry, pitch is 34 samples. So right, another one is a time domain. One is like a time domain autocorrelation. The other one is B is a magnitude spectrum. So you can see they are magnitude spectrum. So maybe they are normalized. Make it bigger. Make the harmonic is bigger. Another one is zero crossing spectrum. So you can see zero crossing spectrum and spectrum correlation. So you can see spectrum correlation. We can find the peak point here. Another one, they try to say our T0 will be bigger. So you can see in the spectrum correlation, so they will be in frequency domain, they will be find a little bit close to double frequency. D is spectral autocorrelation, and C is zero crossing spectrum. So you can see B is magnitude amplitude. So sometimes you can see the magnitude of a spectrum. You can see this one is your like you can see here we are trying to find will be close to find the double. You can see this one is similar, right? We are find double pitch here. So this one not just only one winner, because our speech frame is become T0, your speech signal, the pitch is smaller, so you can see we are frequency domain, we just find one winner. If the pitch become the bigger, so you'll be similar like we have another small one. So this one you can see we are find one half of pitch. This one around 60. This one could be around one half of your pitch here. So in frequency domain, we are easy to find. Will be easy to find half of pitch. In time domain, will be easy to find the double pitch. So you can see they give you more clear example here. So this one, A is original signal. A is your original signal. So you can see A, this figure, first one, their pitch is 32 and 59 and 100. So you can see 32, the frequency is higher, pitch is smaller, and 59. So this waveform, the pitch is 59, and this one pitch is 100. So the pitch is 100. And first one, we're using the temporal autocorrelation will be time domain. Time domain, we are using normalized autocorrelation. So you can see the winner. Oh, well, we are 30, we are 32. So 32, you can see we are 32, 64, and 96. Oh, we have a winner. So you'll be one pitch, double pitch, and three pitch. And then up to the 59, so you can see we are find two winner, almost two winner. If the long pitch, so you can see our pitch to 100, we just in temporal time domain with autocorrelation method, temporal autocorrelation method, we only find one winner. So in spectrum domain, spectral autocorrelation, you can see we are only one, like a pitch 30, 36, 32, so in 5 or one pitch. And if we are using up to the 59, your pitch is 59, so you can see we find one and half a pitch. And then if you are 100, so you can see 100 around 50, 25, and 12.5. So you can see in frequency domain, they are easy to find. So if we are using time domain, because we are using the in time domain, most of them we are find pitch. It's more like a waveform. Try to move your speech frame. Try to find the similarity. So that one time domain find the pitch easy to find T, 2T, and 3T. So if your pitch is smaller, so easy to find 2T and 3T. So, however, if you are using the frequency domain method, so you are trying to find harmonic frequency. So you are easy because you are easy to find the fundamental frequency is 2f0, 3f0. But in time domain to look like this one is t over 2, and t over 3. So if you are in frequency domain, if you are doing the pitch, so you are also similar like time domain. We try to from the waveform to find their periodical signal, and also try to model their pitch their harmonic information. Most of them you'll be find f0, 2f0, and 3f0. However, look back to the time domain. That one is pitch, a half of pitch, 1/3 of a pitch. So you can see if your pitch is smaller, you are easy to find 2 pitch, 3 pitch because tau, we are searching the tau from 60 to 160. So if your tau PT is smaller, so you are easy to find 2 pitch, 3 pitch. If your tau should be up to 100, so it's not impossible to find 200 because your tau is searched from 16 to 160. So, however, this one f0 is 1 over t. So that one is 1 over t. This one is like a 2t. This one is 2f0. So it's more like a 2t over it's t over 2, tt over 2. So you can see, and this one is 3 over t. So because your speech frame, if your t become the bigger, your f0 becomes smaller. So you are easy to find 2 f0, 3 f0. So you can see they are a little bit different. So contradiction. So in the high pitch, you are easy in frequency domain correlation. So you are easy to find the double, half of pitch, third pitch. So in the low pitch, low pitch. So your time domain autocorrelation easy find the double pitch here. So they are proposed could we combine them together? So maybe some guys say, could we combine them together to make good use each side? So they have some combine, propose some combine, should be somewhere. They propose combine method. So their combined ratio is alpha equals 0.5. So we take the criteria from temporal autocorrelation, a half of them, and spectral autocorrelation, a half of them. So we combine them together, become a new method. So you can see we can avoid a double pitch, a half of pitch. So you can see the winner more consistent. So they try to using this one. So they try to, one is from time domain, get a cost function. Another one is from the spectrum domain. So the spectrum autocorrelation. So you can see spectrum autocorrelation, because what's the spectrum autocorrelation? Spectrum autocorrelation, you can like this one. So because you are harmonic, so if we are normalized again, so we can do the shift harmonic. If you are shift harmonic, they can do the correlation. So if you are shift peak multiplied by peak multiplied by peak, so you can get the maximum value. So the similar in time domain. So in frequency domain, we also can perform the frequency domain autocorrelation. Try to shift your spectrum waveform. Try to align your harmonic signal. So you try to shift your frequency. If the shift the frequency close to omega 0 fundamental frequency, so fundamental frequency, so you can align the peak to peak, so you can get the maximum value. So however, you'll be shift to F0, maybe you shift to F0, so it will be double frequency and one half of pitch. So in this, here you have to remember what's the pitch. Pitch is indicate your signal, the frequency of your gratis vibration. So the pitch. So your pitch. The pitch is related to your vibration of your gratis. So what we have, so if you're from the 8 kilohertz sampling rate, so there will be around 8 sample to 160 sample. So we try to find the pitch we can from the time domain. So they have two methods. One is from the time domain. One is from the time domain method, and another one is from the frequency domain method. So in time domain, most of them is we are using autocorrelation. In frequency domain, we can using the Conc filter. Also, we can using the synthetic waveform similarity to do the comparison. Or we can using the autocorrelation, shift the spectrum waveform, try to align their harmonic value. So in time domain, sometimes if your pitch is smaller, so you'll be easy find the T and 2T and 3T. What kind of condition? And small pitch, so you'll be easy to find T, 2T, 3T. In frequency domain, so if you'll be easy to find F0, 2F0, and 3F0. So that one indicate is T, 1 over T. This one is indicate T indicate t over 2, indicate t over 3. So indicate, say, if you are long pitch, so if you are long pitch, so your fundamental frequency will be lower. Long pitch fundamental frequency will be lower, so you'll be easy find double frequency, triple frequency. So you can see these two, they have a little bit, these two effects, this kind of two phenomena. So there are two phenomena. It look like a phenomena. It look like they're a little bit compensation. They can do compensation. So we can compensate, can compensate each other to make our pitch prediction more reliable. So you can see they propose our cost function, consider spectrum domain, time domain autocorrelation. So maybe we try to using from the time domain, we find the cost function, and also also we consider from spectrum domain. We combine them together so we can compensate. If your pitch is smaller, if pitch is bigger, so we can use in the time domain and frequency domain together, so to find the pitch. And because we are using the cost function from time domain and frequency domain, so they are a little bit compensate each other, so we can make our pitch prediction more reliable. Here, alpha they are using 0.5, so this main idea here. So you can see more clear. You can see from this figure. So we are combining two together. So temporal domain can make a good prediction in long pitch. Spectrum domain can make a good prediction in short pitch. So they have a there are two benefits from different point of view, from different points. So we can combine them, their advantage together, become the combined cost function. So you can see we can make our pitch prediction more reliable. Okay. The other one, they are talking about a lot of different approach. So this one is not our focus here. So they're talking about like a spectrum. One is a spectrum autocorrelation. Is another one is spectrum synthetic. Spectrum synthetic here. So we can combine because one is a spectrum autocorrelation, another one is a spectrum synthesis method. So we can combine them together and using because their cost function is not just linear combination. It's not just linear combination. They are using more like a multiply. So they, according to the reference paper, they are using the multiply and using the beta, but they didn't give me the physical meaning. But this one you have to go back to check their paper to know why they are using this combination to become a new cost function. So you can see one is spectrum synthesis, another one is spectrum autocorrelation. So they can get a little bit, combine them together. They can get a little bit reliable. You can see a little bit reliable performance, just for you to understand it here. Another issue, because we are trying to find a pitch. So pitch range. So here is a 15 to 150. In the previous section, they're talking about around from 16 to 160. So spectral analysis conducted by 240 Hamming window. So you have like this one is more like a pre-processing. So you can see, so if we find a pitch, if we remove your long-term, short-term prediction, so you can remove, if you have removed some information pre-processing. So they are trying to find the best weighting function for the combination. When we're talking about the spectral autocorrelation and time domain temporal autocorrelation, the other one is a synthetic spectrum and spectral autocorrelation method. What's the weighting value, the best weighting value? So they just do a lot of simulations. They have according their test pattern. So it's not a 0.5 is the best. Should be according different versions. So it will be close to around here. This one just they do more simulation to find the best value, combination value here. This one just for your idea is not a big deal. Another one, because what we're talking about, because if we are trying to find a big pitch, did you remember previous section what we're talking about? If we have the speech signal in harmonic, in frequency domain, they can be drawn like this way. So you can see they have an envelope shape. This one related to your LPC. So if we can remove LPC, make your signal harmonic like this one. So if you make your signal like this one, so you are easy to find your pitch. So however, if you are trying to do LPC inverse, sometimes will be take a little bit computation. So however, in your application, we do not to calculate LPC. How to perform to remove the envelope shape. So they have some simple way to do spectrum filtering. So okay. So before we talking about this one is another example. They are using many combination. Okay. So they are using different pre-processing filter, pre-processing. This one is try to using many pre-processing. What's the pre-processing? For example, if you have speech signal like this one, in the past, what we did is whole waveform move the tau and try to match here. So we have to move this point to this point. What we did before. However, like this signal, could we do the pre-processing? We have like this signal. Okay, so if we can do some pre-processing, we truncate this one out and become your signal like this one. So that one we are truncate in the middle. So make you try to do the pitch prediction. The noise become lower. So this one is more like our pre-processing. So you can see here they're using many flattening technique to try to do some simple pre-processing, make your pitch prediction more reliable. So in the last previous chapter, what we're talking about using LPC inverse filter to multiply your time domain signal, make that speech frame become no envelope shape. So you are trying to find pitch more easily, more reliable. However, if you do not have an LPC coefficient, so maybe easy way you do the preprocessing, truncate in the middle, try to find the dominant signal according your dominant signal to do the pitch prediction. So it's the main idea here. So another one, in the textbook, they talking about a little bit detail, another point. So I go back to here. So from this figure, they try to show many different approach. So A is a female speech. B is their pitch information. So C is time domain autocorrelation. D could be is another weighted WTA. So I have to double check. So E is a spectrum temporal autocorrelation. This F is a synthetic spectrum and spectrum autocorrelation method. Another one is WSS, and that one is spectrum synthetic synthesis spectrum autocorrelation method. So another one WTA. So they should be defined. One is spectrum temporal autocorrelation. Another one, what we're talking about is temporal. So they have many abbreviation here. This one, spectrum similarity, they're using SS. This one is a harmonic peak detection. They are not using this one. So most of them, they're talking about SS. This one is we are talking about time and frequency domain. So this one is a time domain temporal autocorrelation, TA. Another one, this one we're talking about spectrum temporal autocorrelation. And then ST is spectrum temporal autocorrelation. So spectrum temporal autocorrelation. So you have a temporal autocorrelation and spectrum autocorrelation, spectrum and temporal autocorrelation together. And the other one we call the spectrum synthesis method. So this one is another spectrum synthesis pitch prediction. They introduce another one. So they're using the sync function. To synthesize your waveform. Try to and then they come out synthetic synthesis, and this one synthetic synthesis and synthetic spectrum autocorrelation. So this one they call SS is spectrum synthesis and spectrum autocorrelation. So SS. And also they are using like this one. So the term spectrum synthesis, spectral autocorrelation. And then here they're talking about TA and W. They put a W here. Should be somewhere. W should be weighted. Also. So figure 612. I double check. So they're talking about temporal autocorrelation, WTA. I have to double check WTA. Should be somewhere wrong. They didn't give me the. So this one they're talking about the best weighting value because they combine them together, plus alpha and beta can get a better performance because they combine some because spectrum synthesis and spectrum autocorrelation is spectrum autocorrelation is based on waveform correlation. This one is based on synthesized waveform similarity. Try to see which one is more close. And this figure is show we are based on female temporal autocorrelation. This one I have to double check. During the break, I have to double check what's the W abbreviation. So E is a spectrum temporal autocorrelation. F is spectrum synthesis. And WS according W, F, G is a little bit, W could be is more like a weighting. And later on you can see the winner is H, spectrum synthesis and spectrum autocorrelation. And the other one, this one, according another pattern, is male speech. Male speech, they have a big wave or big pitch. Female, the pitch is smaller. So you can see their temporal autocorrelation sometimes will be better. The frequency domain could be a little bit worse. So you can see their speech synthesis and spectrum autocorrelation, they are preferred winner. So this one is their ground truth. So C is the temporal autocorrelation, and E is spectrum temporal autocorrelation. This one, spectrum, and also synthesis. So they try using different combination and then to see which one is the better. So most of them, they are talking about different combination. So you can see example pitch contour variation pitch detection algorithm. So in figure 612 and 613, so they are pitch error. So you can see pitch error in strong voice region are reduced and combination time frequency domain. Most of error occur speech onset, offset. So in irregular pitch pass, so will be happen. So you can see they just say what's the pitch error come out. Most of them from the voice to unvoiced. So you can see voice to unvoiced. This one is onset, unvoiced to voice. So onset sometimes will be make some error prediction. So you can see the error, most of the error will be come out is around the onset offset. Okay, so WTA I have to double check, and also WSS is more like a little bit filter, weighting, like a weighting filter, make it look like better. And then you can see WSS like G. So they have some smooth. I'm not sure. I have to double check the abbreviation here. I'll talk to you next lecture. So this one is not big deal here. The important issue here, they try to combine time domain and frequency domain to get a better performance here. So another one, if we know, because the speech signal, they have many harmonic signal, we have an envelope shape. If we can remove the envelope shape, so we can make our signal easy to do the spectrum or time domain to do the pitch. So they are considered, if you are not, if you are application, we do not calculate LPC, how to do the pre-processing. So one easy to do the pre-processing, we can use in the click. In the middle is not important. We try to keep the dominant value. So you can see if we are smaller than that one, we keep that one. If it's bigger than that one, we are summation. In the between, we are make them to become 0. Or the other one, we can say we can using this one is one clip. The other one, we are keep original value, or we keep the 1 and minus 1. So they have a 3 different clipper function. So this one is your original signal. So first one clip signal is more like this one. And second clip function is like this one. The original offset will be kept. And third one will be more like a +1, -1, +1, -1. So they using original waveform do some pre-processing to get the signal. Based on the normal pre-processed signal, we try to find the pitch. So that one could be make your pitch more reliable, because sometimes we have a lot of noise, so you have an envelope shape, so you can make them more robust. So you can see here for high pitch speaker, the difference in performance scope between various clipping combinations are small and probably insignificant. If you are high frequency, so high frequency is look like a high pitch. So high pitch is like your pitch is bigger, long pitch. So you are, because this one is longer, so you are do the center clip, maybe not big issue here, but pitch is more closely. This one is bigger. High pitch speaker maybe did not make a big difference. Low pitch sometimes will make a little big difference, because you are remove some redundant, some small noise, and make then overall performance become better. So this one, so what they did. So the key problem in center clip is choice clipping threshold. So how to determine the threshold is very critical. So the threshold for clipping are set around 30%, maximum absolute value. Some paper they propose. So you can see the difference in performance remaining. So they have a different combination to do the center clip, and then try to find which one will be get a better performance. So they are already in the later on, they give you some performance table here. Another one is called the pitch track. So pitch track will be later on what we will be talking about next section. So right now, what we're talking about here, we are talking about pitch prediction, and then you have to remember what's the pitch. So pitch is like a gratis vibration. So a human being is a pitch period have some fixed area. One, we can from the time domain to find the pitch. So if your pitch is smaller, so small pitch will be easy to find double pitch, triple pitch. So in frequency domain, if we are waveform transform to the frequency domain, we are based on frequency domain waveform, so we can easy to find, because we are based on frequency domain waveform to find the pitch. Under that kind of condition, so you'll be find fundamental frequency F0, or sometimes you'll be find fundamental frequency 2F0. So 3F0. 2F0 is related to your pitch over 2, half of pitch, 1/3 1/3 of a pitch. So you can see two different approach. They have some issue over there. So if we consider combine them together, can sometimes can make your pitch prediction more reliable. So according to what they propose, they are consider many different combination, try to find the better performance here. So they show you a different approach. So in the past, while we talking about how to find the best pitch, sometimes we try to remove the envelope shape. So envelope shape in frequency domain, you can see more like this one. However, in time domain here, this one, in time domain. So if you are in time domain, LPC inverse, so you'll be more like a more regular. So you'll be more like high frequency domain become this waveform. So we are best in time domain. Sometimes it's easy to find a reliable pitch. In frequency domain, you also can find reliable pitch. However, some application we are not well known the pitch information LPC. We are not calculate LPC coefficient in advance. So we can do a simple pre-processing. So they call the center clip. They call the center clip here. So they try to using this three approach. Try to keep your time domain more dominant turn. And first one is look like in the middle become the zero. And dominant part will be keep their shape. And the other one, they are keep original value, and the other part will be zero. So the other part will be zero. This one original amplitude. This one will be cup, then become the cup, then in the middle become the here. And last one, if we are over the threshold, will be 1. Under the threshold will be -1. How to determine the threshold? Here they propose, some paper propose around the 30% your maximum amplitude. So around that one. So they say based on this one, so you can get sometimes performance a little bit better because it remove some not so important dominant term, but they have some impact here. Because if you are high pitch is like a mare, the pitch is longer, maybe not big difference, but it's a low pitch, high harmonic, high fundamental frequency. They could be make a little bit difference, so make a performance improve. So this one just give you idea. Okay, I repeat here using the Mandarin. OK， 那这一章主要的精神是在做pitch 的预估。那 pitch 的预估，之前的章节只是在 time domain， 那这一章呢有告诉你从 frequency domain 的角度。那 pitch 的精神就是我们的Gratis 鸿门的振动的频率所形成。那我们的 pitch 呢，原则上人类大概16个 sample 到160个 sample 之间。那我可以在原来的录下的音的 time domain 去找 pitch。那找 pitch 的物理意义精神上就是你的从waveform里面去找出它可能的周期现象。那最笨的方法就是 waveform 的移位相似的比较。所以说呢，但移位相似，你移到2个周期呢，如果你是一个sine wave， 如果你是一个 sine wave， 你移一个周期跟移2个周期可能都是 perfect match。那所以说呢，实际上都会有同样的问题。那 所以说在 time domain 容易去找到 double pitch、triple pitch， 在 frequency domain 呢，你找到的 pitch 呢就会是因为 frequency domain 你可以用梳子的方式梳子的方式，用合成的 synthetic 的方式，或是 frequency domain 的 waveform 的 auto correlation， 以你的 waveform 去做 correlation 用合成 synthetic 它课本有提到2种 synthetic 的方法，一个用 sigmoid function 用 sinc 那种叫做 sinc function， 就是你们在数学上的这个 sinc function 就看你这个下面多小sinc function 去做合成你的 waveform。 那其次的话就是说你用这种去做合成，就代表你这个fundamental frequency 多宽那就有时候会找到 f0、2f0， 但 2f0 代表的周期是t， 3f0 代表的周期是t。那所以说频率 domain 去找 pitch 的时候，容易找到 long pitch，time domain 容易找到两 pitch 是多倍频的多 pitch。那所以说课本的例子呢，会有秀出说，如果是短 pitch 32的时候，你在 time domain 容易找到倍频率，然后在 long pitch 的时候不会，100的时候不会。frequency domain 呢，在 low pitch 32的时候不会找到，但在100的时候容易找到50、25诸如此类。那课本呢就会有说，我能不能把2种方法做结合？那它的结合有结合pitch 时域轴的auto correlation 跟频域轴的 spectrum correlation。那它中间又提了一个合成的 pitch 跟 spectrum auto correlation。那它这2种方法，或许说它用的方式不是用相加，它是用相乘。那最后他做了一些分析比较那基本上实际上要找精准 pitch 有各种不同的方法，那你要记住到它的物理意义。那课本在做一个 example 的时候，有一个比较重要，就是说 pitch 经常会误差错误比较大的时候是在 onset 跟 offset， 也就是有声到无声，无声到有声，因为那时候 pitch 的变异性比较大，那声音的那个周期相似性没有，那比较不容易去抓到周期的现象就不容易抓到正确的周期现象。那另外一个呢是说，那我既然以前我们说过，如果我的音进来之前，我能做一件事情，做什么呢？能把它做那个去掉 harmonic， 去掉这个 waveform 的 harmonic 的 pick 点 harmonic 去掉的话，可以让我找 pitch 会比较准。那也就是说，我时域轴是这个，然后我去 LPC 的 filter 可以让这个 amplitude 呢变小，只要比较秀出你的 pitch 的 dominant 讯号。那另外一个呢，如果从频率 domain 它这里有 envelope share， 这个到频率 domain 比较没有 envelope share， 那我用我刚才所讲的时域轴找 pitch， 频率轴找 pitch， 它比较可靠。那另外一个呢，如果我的应用呢并没有先找 LPC， 我没办法做 LPC inverse filter， 那这时候怎么办？这时候我就必须要把中间的讯号能不能只要保留，它叫做 center clip 中心点的一个 clip 掉，把中间的东西能不能拿掉？他提了3种方法，这3种方法呢，3种方法主要的精神呢就是第一种方法呢，原来的中间的讯号 center 掉的话，只保留上下，那把中间变离，上下减掉这个差值，变成都接近原点接近0这边变大。另外一个呢，保留原来的 amplitude 中间清零。那另外一个呢，大于它的 threshold 就是正1、负1、正1、负1，这样去算 correlation。那另外也就是说，这种呢在 long pitch 的效果并不显现，但是呢short pitch 也就 fundamental frequency 高的时候，比较效果会有一点显现。那它有一些好处，也就是说你在算 pitch 的时候可靠度会高一点。OK， this is our first lecture. We just briefly summarize the pitch prediction. So you can see the main idea we are doing the pitch, try to find a waveform of maybe time domain waveform and frequency domain spectrum we try to find their waveform similarity, try to find moving, like an autocorrelation, try to find moving your waveform, try to find the correlation. However, in frequency domain, they have a different approach to the synthetic wave spectrum. Try to make sure your synthetic spectrum similar your original spectrum waveform. So this one, there are different approach. So in frequency domain, we are easy to find like a double fundamental frequency. That one indicate half of pitch, one third of pitch. In time domain, we are easy to find double pitch, triple pitch. So we can combine two approach to make a good use uh, their their benefit, make good use their benefit to do reliable pitch prediction. Okay, so this one is our first lecture. So take a break. So we'll be talk to you around the 15 minutes. Come back around the 5. We are start our second section. So I stop here.